So hello everybody, I'm Marcus, I'm professor here at Texas A&M University, and today I'm going to present this position paper about the definition of the malware detection problem. So to start, I'd like to go with some provoking thoughts, and then we'll dive into the theory of maliciousness, the main topic of this presentation, and meanwhile I'll present some background on hardware performance counters that I use as a problem that highlight some of the aspects that I'll be discussing during this presentation. So to start with this provoking thoughts, I have some questions for you here that lie on the border of the malware definition problem. I'd like you to try to answer for yourself these questions to show if you think that these situations fit the malware definition, if they should be considered malicious or not. More specifically, in this presentation, we'll be talking about the last case, the discussion if a software piece that targets the underlying hardware platform that it runs on instead of the software itself can be considered malicious or not. So this is exactly the case of hardware performance counters, and this is exactly a corner case of the definition problem. So I use the hardware performance counter here as a supporting and as a noticeable example of why we need a theory of maliciousness. Why this theory is required, what is this theory, and how can we advance toward this direction. So since I use the hardware performance counter as a kind of a noticeable example, I'd like to give you first some background in the hardware performance counters that are basically hardware sensors present in all modern processors that count for metadata. While the software is running, it's counting architectural events like the number of branch is predicted, the number of cache misses, the number of pipeline stalls, executed instructions, memory access, all this sort of architectural information. The original design of these counters was for performance monitoring to identify bottlenecks during a performance evaluation. But many security researchers propose to use these performance counters in the security domain, more specifically to detect malware. So the idea here is that we can rely on the data collected by these hardware performance counters to establish profiles of what is considered normal execution and malware execution. So the underlying idea here, as shown in the graph, is that we can separate malware and goodware based on the architectural execution profile. If that's true, it would be very good because we would have found a very efficient way of detecting malware, because these counters operate at the hardware level, they are present there, they do not impose significant overhead to the software execution, so it would be a very efficient malware detector. But then we have to discover what are the limits of this technique, what are the capabilities that this technique really presents. So that's basically what authors have been doing, what researchers have been doing, applying the scientific method to discover what are the limits of this kind of metadata-based techniques. And if we look to the current scenario of all these studies, we can notice that some justified controversy about that, because the results are very diverse. So if we look to some results in the field, we notice that they use different metrics, each one to evaluate the feasibility of these approaches. And among these metrics, there are significant variation among the results. So it's hard to establish some kind of ground truth for evaluation. Even worse, we notice that based on this myriad of different results, some authors decide that these results showed the feasibility of the approach, whereas some other authors decided to claim that these results show exactly the opposite, the infeasibility of this approach. So it seems there is some justified controversy about that. And I believe that if we had a theory of maliciousness, it would help us to disambiguate, to solve this controversy. And I'll show you how. Well, if we look at what are the reasons behind the authors giving these distinct verdicts, we basically find two main issues. The first one is the nature of the problem. So some authors believe that there is no significant relation between the malicious actions executed at software level and the metadata collected by the counter. So there's not a one-to-one mapping between software and hardware events. They certainly have a point. But on the other hand, some of the results showed already that hardware performance counter might be effectively capable of detecting malware based on these high accuracy results. So if that's true, one use hardware performance counters for malware detection, regardless if we have a greater explanation about what it's being detected or not. So it turns out that's more methodological problem. Like we must show that this approach is feasible. If it's feasible, people use it regardless if we know how to explain how it works or not. What are the exactly correlations between software and hardware? Up to the moment, we do not have such established high one-to-one mapping. On the other hand, if we look to the methodological problem, we would like to have kind of strong evaluations to be able to give a final verdict if it's possible or not. But if we look to the current scenario, all the same paper, there are giving different verdicts about the feasibility of hardware performance counters, and notes that some of them are really methodologically limited. They are using a very small data set size to conclude that malware detection by hardware performance counter is feasible. On the other hand, the same approach that are criticized in this one use also small data sets, sometimes even smaller than the works that are criticizing. So the current scenario is a little bit blurry, so we need more stronger evaluations. So what I would like to say up to now is that even if you do not have such a strong and robust evaluation, if this strong evaluation is still required to prove the feasibility or not, something that might help us to solve this discussion, solve this controversy, is to think if we are looking to the hardware performance counters problem in the correct way. For instance, look into the same first issue once again about the relations between hardware and software event. Maybe the best question is not to think if hardware performance counters are simply great for malware detection or not, but to ask, what are hardware performance counters great for, right? So I think we should have a distinct view on hardware performance counter. And this is what I'm going to present right now. So we can basically divide malware, at least in my view, between those samples that are more focused on the software abstraction and those samples that are more focused on the hardware abstraction. So the first of them focus software artifacts like process, file, and other software abstractions, and the other class focus on hardware abstraction, side effects, architectural impact. So usually when talking about malware, and most of these previous studies talking about HPC are talking about the first class. These are the majority of malware that we know by nowadays. Software-based, software-focused malware sample, the traditional malware samples. But we also have this hardware focus, this architectural focus malware sample. You should not neglect them. And one might be wondering, well, but do these kind of a sample, kind of attack really exist? And in fact, if we look at some recent attacks that are reported in the literature, what we can find is that many of these attacks exist. For instance, the row hammer attack. What happens that in the software running in the system is not directly targeting other software PC, but it's targeting the underlying platform. It's trying to exploit a characteristic of the DRAM memory, trying to make the architecture to flip a bit. And then based on this bit flip, it might, for instance, escalate privilege, become admin, and then perform other ordinary malicious tasks. So there are some malware pieces that target the platform, as the row hammer attack, as I said, as a dirty call, and many other attacks. And more than that, hardware performance counters are a suitable detection to detect this kind of attack, since these attacks are based on the interference with the hardware architecture, and hardware performance counters are monitoring architectural events. We can use these hardware performance counters exactly to detect this kind of malware. So maybe a solution for the malware problem as a whole is not to substitute one technology by another, but to use complementary solution. So this is exactly what we would like to understand. If we use hardware performance counters in conjunction with traditional detectors, do we achieve a greater detection? So basically that's what we did. We developed a test for that. So we compared the detection rate of a typical machine learning detector based totally on software that's classifying the execution of a software with hardware performance counters. A new detector, a typical detector proposed in the literature for hardware performance counters that's classifying architectural events. And we have very interesting results because at the first glance, if we look to the single result of the classification of all malware samples in our data set, we note that, as reported in previous work, typical machine learning is better to detect this kind of sample because they operate at software level. But if we start to separate what are the samples that cause the side effects, the harder focus malware sample, from the soft that do not cause side effects, these more softer focused abstraction malware samples, we note that basically the whole detection capability of a traditional machine learning software implemented detector comes from these software-based samples. Whereas the whole capability of detecting or significant parts of the detection capability of harder performance counter comes exactly from these harder focus malware samples, as we hypothesized. And more than that, if we combine these two approaches, detecting side effect sample using harder performance counters and traditional software-based malware using traditional typical machine learning models, we can have a detection rate, a detection accuracy that is greater than all of the detectors combined, all the detectors alone. So the combination produces a greater result than any of the detectors alone. So maybe the solution for the problem is to combine detectors. So maybe when talking about harder performance counters, we are talking about another detector and not a substitute detector. Okay, I talked all about this so far to make another question. How could have done this before? And every time that we have another detector, do we have to use them in conjunction? Is this always the best solution? And I think that the theory of maliciousness would have answered all these questions. So let's talk a little bit about what is a theory of maliciousness. So first of all, why do we need this theory? Because I think that this kind of blurry scenario between what is considered malware and it's not is very common. It happens here in the case of harder performance counter, as I demonstrated, and it happens a lot of time in the literature. Most of us, malware researchers and security researchers in general, we have some practical definitions of what is malicious. We all know that something undesired, but we do not have formal foundations for that. Even if we look to NIST documents that are supposed to provide standards, we know there are multiple definitions of what's considered malicious or not. So my point here is that we should go from these practical definitions to some formal definitions to have our evaluation. So we should better define, for instance, what we consider malware. So it's important to talk about what is a theory of maliciousness. It's important to clarify that it's not only a matter of a new taxonomy to stating that, oh, now we have this taxonomy classifying, oh, malware, harder focus and softer focus. It's not only a matter about a new taxonomy, it's a matter of defining what we consider malicious, why do we consider malicious, and how do we approach that? How do we consider a successful detection successful? I mean, we must have a plan to consider something malicious, to handle this maliciousness of this piece of software, piece of hardware, or piece of any other object, and how do we evaluate that if we succeed in our test of handling it? So all of this is part of a theory of maliciousness. Of course, we'd like to present to you right now a theory of maliciousness, but this might be impossible, or is at least not possible for us right now, because as you might imagine, as you saw in the first slide, it depends on answering lots of corner case, a lot of conditions on the border of the problem. This might depend on the context, and this might depend on a community effort of the whole security community to work on it. But definitely we have some hints of how a theory of maliciousness would look like. So I'd like to present you some of these hints. So I think a good idea to evaluate if a solution is good or bad and what we are trying to achieve when we are detecting malware and any other malicious activity is to introduce the concept of attack space reduction. So the idea here is to think that for every object, for every artifact, either a software piece or a hardware piece, we have a space of activity that can be performed over this object, over this artifact, as you can see in the first figure, in the figure A. And we have many dimensions of this problem because we have many implementation possibilities, we have many ways of acting. Here I'm representing two dimensions. One is software, another is hardware. So between this space formed by software and hardware, we have many possibilities. And initially, as you can see in the first figure, basically a software can be, or a PC of malware or whatever, can be spread all over this domain. There is no limit for what you can do with this given domain of hardware and software. But we want to separate malware and goodware, right? Malware and benign software. So basically, when we apply harder performance counters or machine learning, as you can see, we're basically constrained the possibility that one can perform over this space, as you can see in the central figure, the figure B. So basically what we're trying to do is to constrain the possibilities that one has over a single space. So I think this is a good definition of security, of what we are trying to achieve when handling malicious behavior in general. We are trying to constrain the possibilities. Obviously, you can see there's still malware software in that space, right? Because it's completely impossible. It's naive to believe that we will, with a single solution, eliminate completely malware from our lives. But basically, we are constraining this mode of operation, the action that the malware can perform. And of course, it also provides us a way to evaluate if we have a better solution or not. Because intuitively, if we have another solution, basically, it's better than this current existing solution if reduces even more the attack space. But there's still a remaining problem with this definition. So when we should use a complementary solution, like hardware performance counters and machine learning solutions, like I show in the third figure. So if we use hardware performance counters and typical machine learning, we are constrained even more this space. And now in this case, we succeeded in separating all the good files from the malware files when it is suitable. Well, according to this hint of how a theory of maliciousness would look like, basically the idea here is that they are complementary approaches if they constrain the attack space in different directions, in this case in orthogonal directions. So basically in one direction, we have hardware performance counters constrain the device one direction, and the other dimension, we have typical machine learning constrain the malware the attack space in other direction. So basically, this is the case when we should use complementary solution. And this was exactly the case that I demonstrated via hardware performance counters. So hardware performance counters and typical machine learning are complementary solutions. But now we have a more formal explanation of that because they are constraining the attack space in different directions. So this is what I'd like to present. Before our conclusion, I'd like to state that this kind of more formal evaluation is part of an effort that many researchers call the science of security. This initiative to establish more formal foundations, yet a very practical one for security problem. We believe that this is a way to contribute, even though a little bit, to advance, to move our field forward. And we have many criticisms to our security solution, as you can see here, either hardware performance counters or any other security solution. We believe that many of these criticisms, many of these weaknesses of our current developments can be at least mitigated via more formal definitions. And I demonstrated that via the case of hardware performance counters. So basically, as my final words, I'd like to say that we demonstrated via hardware performance counters how a theory of maliciousness would have helped and can help from now to the future to disambiguate this controversy about that, so we can make better question and establish when a solution is complementary and other when a solution is better than other. For the specific case of hardware performance counters, they are a promising solution. They must be better evaluated. Of course, we need stronger results, but more than stronger result, we need another view about the problem of malware detection problem, about the detections, about the hardware performance counters as detections, and more specifically, we believe that the combination of the typical machine learning and hardware performance counter might be a way to move forward. And this might apply not only for these hardware performance counters, not only to the malware detection problem, but to many techniques and solutions that are proposed for a myriad of security problems and security applications. So I hope to have fostered this little bit of discussion. Of course, this is just, as I said, a position paper, initial thoughts about the subject I would like to discuss more. So please reach me out via Twitter, via email, on my website. I'll be available here for answer your questions. And I also have positions for PhD students and other students interested in this kind of subject. So if you are a student, either research in this more high-level theory of maliciousness, or if you are more interested in developing this more robust evaluation using hardware performance counters, all this kind of low-level stuff, I'll be very interested in chatting with you. So thanks a lot.